came in late, I talked about the project. Make sure you have that on your horizon. It's due at the end of the semester, but it's an important part of your grade. Alrighty, people. If you have any questions about the quizzes, please see me afterwards. That's quiz number 4. I'm almost absolutely certain that we'll get at least 3. As I said, I guarantee you 6, so we'll get another 2 at least. I'm pretty sure we'll get 3. I'm going to try to push for 4 more quizzes. So the more quizzes we get, the better for you, because you can drop those lower ones. You did great? Oh, sorry. Yes. All right. How are y'all studying for the quizzes? What do you do? If you're really sick. Huh? Okay, yeah, the old quizzes are a good way to study. In fact, I would take the old quizzes as you're reading through the book and look for the answers to the questions. That might be a good way for you to study as you go through. I write new questions often, but it helps you as a guide to go through the reading, to pick out the points that are usually the big ideas that I'm looking for. Okay? Any questions? All right. I have a few clicker questions, and then I think we're done with this chapter. Yeah, we are. We haven't done these, have we? Let's do this one on the upper left. The tonometer is used to measure pressure in the fluid. In which of these places? The synovial joint, remember there is fluid in between the joints in the synovial joint. In fact, you can replace that fluid. They take a needle, and they stick it in your knee, and they inject additional fluid into the synovial joints. The brain, that's the CSF. The eye, remember, had 2 different types of fluid. And then the bladder, of course, you know, fluid in the bladder. All right, let's stop at 46. Did you get clicked in? Mm-hmm. All right, 50, I'll stop. Okay, good. It's the C, right? Remember the little beagle, right? The tonometer where he had the magnetic pin. Usually the tonometer is a burst of air. That's what they use usually at your optometrist. So the answer is C, I. Glaucoma is the result of what? This question. No, it's okay. I understand. All right, let's stop at 30. Yes. Okay, A is right. And the brain and central nervous system are protected by cerebral spinal fluid. Condition known as hydrocephalus is the result of what? All right, let's stop at 30. Right, very good. B is right. And then one more. What part of the eye is continually replenished? Alright, let's stop at 22. Hey, good morning. Alright, let's see. It is aqueous humor. I know it can be difficult to keep these two straight, but remember in an eye, looks like this. The vitreous humor, virtuous is not virtuous, huh? Yeah, the vitreous is right here. The aqueous is right here. And remember, the glaucoma, many of y'all got this, the glaucoma results when this pressure is too high. So over here, the answer was A. It wasn't B. However, if it said block drainage of the aqueous humor, then it could have been B, because that's how glaucoma usually occurs. Because the fluid in this part of the eye drains and is replenished. It drains because it gets rid of waste, and then it's replenished. It brings nutrients into the eye. But if you block that drainage, then you can get an accumulation of too much fluid in the aqueous humor. So maybe draw a picture, put it up on your bathroom mirror, sort of keep those straight if you're finding that difficult. Well, I don't know. I mean, everybody's a little bit different. I know when I'm trying to learn something, I usually associate it with something that I know really well. I don't know. It's how do you learn things like that? Yeah.
A comes before B, and A is the front of the eye.
There you go. That's a good way.
Water, replenish.
Mm-hmm. Yes, all those are great ways. So those are little tricks that you learn to, to cement things in your mind. All right. All right. Any question about chapter 2 at this point? Of course, the exam will cover what was left of chapter 2. Huh? Oh yeah, it'll cover chapter 3 too, but not all of chapter 3. Let's see, where did we leave off last on the exam? Do you recall? How far did it go?
So the part that we just finished with, the anatomy part of chapter 2.
Okay, yeah, so it'll be the anatomy part of chapter 2 for the exam. Oh, and then also fluid flow. So if you're in your notes, you're going to be going back to the equation of continuity, because that wasn't on the exam. If you're in your notes, you're on this page, fluids in motion. That's page 20 in your notes. In your book, that's going to be page 41. So page 41 on. And then I'll tell you, probably we're going to do the physics portion of chapter 3, not getting into the body applications. Not going to be a whole lot of material on the test, but I'll try to make it the same length, 40 to 50 questions. I find that's a good length. If you miss one or two, it's not a big deal. I can have a good mix of really easy questions or surface level questions and then more probing questions. It's a week from today. Awesome.
I think we traveled out of in person on Thursday morning.
Okay, we'll talk. Well, it's on Tuesday actually.
On Tuesday, my bad.
All right. So that's awesome. All right. Let's look at energy and work. So, energy is pretty important in physics, and it's certainly important in the body. Energy is the ability to do work. And work is not the type of work that we think of, like you work at a job, or you're working right now as you think about things, as you're taking notes. We usually call that work, but in a physics sense, work is different. Work is done when a force causes a displacement. And you have to have both of those in order for you to have work. You have to have both a force and you have to have displacement. So if I have a force, for example, I'm applying a force to the wall, I am applying a force, but there's no displacement. The object is not moving from one position to another, so there's no work. Or if I have an object that's just moving, like this, there's no force causing the motion, at least in the x direction. So even though it's moving, if there are no net forces acting on it, then there's no work being done. Remember Newton's first law? Remember Newton's first law that if an object is in motion, it'll continue in motion. And so if you have this object that's in motion, but no net force acting upon it, then no work being done. So for work to occur, you have to have both a force and a displacement. Both of those. It's just the physics definition of work. So if an object has force but no displacement, or vice versa, displacement but no force, then there is no work. And displacement, I think I've used that term before, but let me just clarify. That is a change in position. The object has to move from one place to another in order for work to be done. So if an object is moving, it must have had work applied to it. Remember the first law, there's no force acting on a constant speed object, but there must have been in the past. So what I'm saying is if I have an object that's moving at constant velocity, say in this direction, there's no work being done. However, at some time in the past, there must have been work to be done because something had to act on that object to get it up to a certain speed. You follow what I'm saying? It's kind of an important idea because later we're going to say this object has energy. And we're going to begin to say that, well, work is very similar to energy, that work actually causes an accumulation of energy. All right, so work is the product of the displacement, or the distance, and the component of the force in the same direction. And the way that we're going to write that is we're going to say that work is equal to F times D. But it's an important point here that it's not just the force, that it's the component of the force that's in the same direction. So what I'm going to instead do is I'm going to write this as F. I'm going to put a little subscript. F, that's not an 11. That's a parallel, two parallel lines. And so that means that the force is parallel to the displacement. So it's the component of the force that's in the same direction as the displacement. So like in this picture, this is a picture of me when I was a kid. Does it look like me? Yeah. Huh? Yeah, right. So just like, there we go. Oh yeah, now you see. All right, so in this problem, or in this diagram, the displacement is in this direction. But the force, notice, is in some other direction. The force is in this direction. And so what we're going to do is we're going to break this force into two components. If we have a force, we call that a vector quantity, we can break it into its x and its y components. We call it. It has two parts to it. It has one part in the x direction, and then it has one part in the y direction. I'll call this fx, and I'll call this fy. And notice that fx is parallel to the displacement. So in this case, my work is going to equal to fx times d. Now this component of the force, we're not concerned about it for this class, but if you want to actually calculate the force, as we do in our Physics 101 or 201 class, and y'all do it if you take Calculus 3, I think you do vector calculus there, right? If you want to find the x component, don't write this down if you don't want to. Fx is equal to f times cosine of the angle theta. So that's how we calculate that x component. So really this formula, the correct way to write it, and I'm going to put it in parentheses because you don't really need to know this, is f d times cosine of theta. All right? So we have some guidelines about how our force and our displacement are related to one another. If force is in the same direction as the displacement, the work is positive. If it's perpendicular to the displacement, the work is, what do you think? We're going to have a negative and I have a 0.
Yeah.
Both of those are good guesses, like they're good answers. I know that this force is doing what type of work? Positive work. Now, in the next one, I'm going to talk about a force that's opposite the direction of this force. if I had a force that was in the opposite direction, what kind of work do you think it would be doing?
Negative.
It would be doing negative work. Yeah. It's like it's holding back the object. And we'll talk about work in just a minute, as work is what changes the energy. And if I'm doing positive work on an object, I'm increasing the energy. If I'm doing negative work on the object, I'm decreasing the energy. And if I'm doing no work, that means I'm not doing anything to the energy. And so this force right here is not causing any motion in the y direction. And so this force is not changing the energy at all. And so a force that's perpendicular to the motion, at 90 degrees to the motion, does no work at all. The work is 0. And if it's opposite the direction, the work is negative. All right, so I'll just draw a picture to help you think about this. If I have an object like this, I have a force that's causing it to move, or the force is in that direction. The displacement is in this direction. And so I have two forces. I'll call this Fx. It does positive work. I'll call this Fy. It does 0 work. That's not ow, that's a 0. Let me write it out. 0 work. And then if I have another force, I'll do it in a different color. If I have another force, I'll call this F2. It does negative work. All right, so like for example, I like to run in the morning, and my dog, she runs with me, but she's kind of slow. I mean, sometimes she's fast, but she has like bursts of speed. Y'all know people like that? They run really fast for like 2 or 3 seconds, and then they slow down. Well, she's sort of that way. But most of the time when we're out for a long run, she's always sort of behind. And especially when I want to run faster, it's like I have to tug her along. I don't tug her along. Like I run with her at the right pace. I'm not mean to her. But sometimes it feels that way, that she's holding me back. And so she would be an example of this F2, right? A force that's holding me back and making me go slower than I really want to go, doing negative work. Okay? So, force and displacement in the same direction, what's that? Positive work. If they're like this, what is that? 0 work, because the force is not causing the displacement. And then what about this? If they're in opposite directions, what type of work is that? Negative work. That's like a dance. I feel like that should be a thing. I mean, it could be like the next floss. Do y'all know how to do the floss? Y'all don't do the floss, dude. That's like 3rd graders. Do you do it? Huh? Yeah, man. Some 3rd graders, they get zooming on that thing. You ever seen a 3rd grader do it? Yeah, they're fast. All right.
So the example of that using a rope.
Huh? A rope? What about a rope? Yeah, a tug of war. What about it? Yeah, sorta. Like, so in a tug of war, and here's my rope. The people, these people are pulling in this direction. These people are pulling in this direction. And the one that wins is going to be the one that does the positive work, right? And the one that loses does the negative work. Because if you're moving in this direction, meaning the guys on the right would win, then their force and their displacement are in the same direction. But here, these guys, they're really just slowing down the progress, so they're doing negative work. Let's try these questions. Which force here does no work at all? A, B, C, or D? All right, let's stop at 25. All right, good. Right, the one that's perpendicular does no work. And these are all moving, each of the blocks are moving to the left. So our displacement here is in that direction. Now if our displacement was up, then A would be doing what type of work? It would be doing positive work. Let's try the second one. Which force does negative work? It's going to the left. The displacement is to the left. All right, let's stop at 25. B is right. And then which force does positive work? Wait, what did y'all put?
It's C.
Yeah, C, yeah.
I thought that the degrees would still be 180 and 0. And you see what I mean? Like 0, 90, and then 180. If it goes 180 and it's negative.
It's just opposite the displacement. It's going this way and the force is going
Yeah.
this way.
Right, so what you're looking for, let me answer your question in just a second. But what you're looking for negative work is that the displacement and the forces are in opposite directions. And here our force is to the right for C, but my displacement, even though I have this force pulling in this direction, then the object is moving in that direction. It would be like, C would be like this situation. After I get it moved, the frictional forces is in this direction, even though it's moving in that direction. And that what did you say?
I said, I guess I'm looking at the arrows.
Oh, yeah. Yeah, be careful with that. The arrows aren't showing displacement, the arrows are showing force.
So how do you know
Okay.
displacement's going this
So
way?
even though the
Because
little
it
arrow
says each of the blocks moves to the left.
Okay.
All right? Just be careful. Once you get the hang of it, it'll be easy. By just reading these problems and understanding that you need to figure out what is the force, the direction of the force, and the direction of the displacement. That's not what I think you were asking when you were talking about 0 degrees, 90 degrees, and 180 degrees. Isn't that what you said? Listen, we said that work is equal to FD cosine theta. That's where these angles become important, because the cosine of 0 degrees is 1. And if I have an angle between my two vectors of 0 degrees, that means they're in the same direction. The cosine of 90 is 0. And the cosine of 180 is negative 1. So that's where I get the positive, I get the 0, and I get the negative from that cosine term. But again, you don't need to know, we're not going to see the cosine at all on the test. But that's where that comes from. All right? It actually comes from the dot product, so you know what I'm talking about. That this is actually just a representation of the dot product. Okay, so which force does positive work? All right, let's stop at 15. All right, good. But I'm not going to mark it right because both B and D, good job whoever put D, that that's also right. That there are actually two answers for this, that both of these forces will do positive work. Now B seems like the obvious answer, and maybe it is, but this force also does positive work because it has a component that is to the left and a component that is perpendicular. So part of that force does positive work because it acts to the left, causing a displacement to the left. And then part of that force does what? Positive, negative, or 0 work. Right, this one right here does 0 work. Which force does the most work? D, yeah. If we say that they're all the same length, I think that D is actually a little bit longer. It looks a little longer. But if you have all these forces that are the same magnitude, then E is going to do the most work.
So it's
E, yes, let me write that down. So the answers here, the force that does no work is A, the force that does negative work is C. This could be either B or D, and then this is going to be B. Which force does the most work? Listen. How can I make this thing go faster? By applying a force that's like this, where part of my force is in this direction and part of my force is up, or apply my force like this, where all of my force is in the horizontal direction. Which one will make it go faster? The second one. The second one, right? If I'm lifting up like this, I'm losing part of my force by just having it act in the vertical direction. How does Moses make tea? No. He brews it. All right. So this is an important idea. This is the work energy theorem. And basically it says that work causes a change in energy. Now when we talk about work, and later when we talk about energy, that they're very closely related. That if I do work on an object, I will change its energy. I might take away energy, or I might give it energy. But if I do work on an object, applying a force over a displacement, I will change its energy. And negative work takes energy away. Positive work gives energy to an object. And that's where this comes in. And that's why it's important that we have the plus and the minus signs for work. Because if I have positive work, this will increase. This symbol right here, this triangle, is the Greek letter delta. It means a change in the energy. So if this is positive, I get a net increase in energy. And if work is negative, I get a decrease in energy.
so the work energy here is work equals the change in energy.
Right. Mm-hmm. But the statement there is the same, that if I have negative work, that means I'm causing a negative change in energy. If I have positive work, I'm causing a positive change in energy. All right, let's try these questions. So we're reviewing work. Is it possible to do work on an object that remains at rest? Stop here in just a few seconds. 43, I'll stop. B is no. That's right. Because if it remains at rest, even if you apply some force, say 10 newtons or whatever, if it's at rest, that means that the displacement is 0 meters. And since work is equal to force times displacement, that means that it'll be equal to 0. I can still have a force, but do no work. Push on the wall, there's no work because there's no displacement. What about the second one? Box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? All right, let's stop at 25. All right, good. C is right. Friction almost always does negative works. If you recall, the frictional force opposes the direction of motion. So usually the displacement will be in one direction, and the frictional force, which I write as a lowercase script f, is in the opposite direction. So frictional forces almost always cause a change in energy that's negative. Did this before, but if I push it, it slows. That it slows down things. That's why Aristotle, we talked about Aristotle, that's why he thought that things always, that they had this natural state of being at rest. However, sometimes frictional forces do positive work. When I was a kid, I don't think y'all do this anymore, but when I was a kid, a common way of getting around our community was to ride on the tailgate of a truck. Did y'all do that? Y'all still do that?
No, that's dangerous.
It's very dangerous.
We do that in the home country.
In the home country.
Mexico.
Are you from Mexico?
Yeah.
Really? I didn't know that.
Yep. I know. Who to guess?
Huh?
Who to guess?
Never thought about it. Anyway, ride around on the tailgate. And what is, if you're riding around on the tailgate, you got your dad driving up in the front of the truck, driving through the field or whatever, what is it that's holding you on the tailgate?
A prayer.
Hanging on. Well, we didn't even hang on. I used to drag my feet on the ground. I got to do this, you know. But friction is what holds you onto the tailgate. And what is the, yeah, and what is the direction of the frictional force? If we're going in that direction, is my frictional force in that direction?
Yes.
No, it's not down. It's going to be that way, yeah. If think about it, if my frictional force was that direction, it would just push me off the back of the truck, right? But the frictional force, I would have a tendency to slide off of the back of the truck, but the frictional force opposes that tendency for motion, yeah, because of inertia. All right, so the frictional force in this case actually does positive work because it causes you to move in that direction. You didn't know that, did you? Like you always thought that friction does negative work, but there are some special cases where it does positive work. So next time you're riding on the tailgate, look next to your cousin or whoever's right next to you and say, man, I'm glad that this friction's doing positive
That
work.
has more to do with the fact that you're on an object that's moving in one direction, so like the friction kind of ends up going in the opposite direction also.
The friction opposes, I know we say it opposes the direction of motion, but in this case when you have friction of an object that's not moving, like you,
Right, but like the truck's moving in one direction, and so you move because of inertia. You resist that motion, and then friction kicks in and moves you back into that motion. If I'm thinking of this correctly.
yeah, I don't think you're saying that right. What's that? What about a roller coaster? Yeah.
It's some part, it's not when we're going up.
For the friction? Yeah. Don't sweat it too much about the friction. But as far as we're concerned, friction will always do negative work. I just want to, because we ride on the back of tailgate, just wanted to tell you that in that case it does negative work. But you won't see that on the exam. Okay? Alright. What is it?
What if something else is pulling at the same time?
If you had multiple forces? Good question. Yeah. That's a good question. Well, it's important, actually.
Is that like the next question or something?
No, but let me just clarify. Because we've really only been dealing with one force. So let's say that I'm an object that's moving with a displacement in that direction. It's moving from left to right. And there are two forces acting on it. There's some force here, and then let's say that there's some frictional force. In these cases, this force is doing positive work, and this force is doing negative work. Now, if the forces are equal but opposite, then how's the object going to be moving? Not moving at all, right? If I have two forces that are pushing on either side, it just stays where it is. And in that case, I would have equal amounts of positive and negative work, and so I'd have zero work being done. Because the net force, let me write this down, if F and big F are equal, and opposite, the net force equals zero. So work equals zero. Ready?
I was just piggybacking on what you said, because like sometimes, people have like boats or whatever it is, so like if you were moving and the boat was moving at the same time, you would have no net force.
Right. All right. That is cool. All right. So kinetic energy is the energy of motion. Kinetic energy is equal to 1/2 mv squared, where m is the mass, v is the speed, well, no, we can call it velocity. We haven't really distinguished between speed and velocity, but speed is like the magnitude of the velocity, so there's no direction associated with it. Just think of it as the speed for now. Notice here that the kinetic energy, if I plot kinetic energy and v squared and v, then it's going to look like this. That as v gets big, as v increases, the kinetic energy increases more. In fact, if I double my velocity, for example, if I double my speed, then I'm going to see an increase of 4 times. If I triple it, I see an increase of 9 times. If I quadruple it, I see an increase of 16 times. Because it's a squared velocity, the speed is squared. This is a quadratic equation. And I said this before, but let's write it again. If you do work on the object, the energy changes. And this is called the what? That's the work energy theorem. It's a simple idea, but it's a very important idea. That if I do work on an object, then the energy of that object will change. All right, you push a car at a constant speed. What is the work done? I'm gonna qualify this just a little bit. I'm gonna ask you a couple questions. What is the total work done? Okay, so if I'm pushing a car at a constant speed, what does that tell me about the net force on that car? I want you to think about that. If I'm pushing it at a constant speed, think back to our Newton's second law. F equals m times a. This is F net. I'm looking for the total work. The total work is equal to the net force times the displacement, pushing this car along at a constant speed. What does that tell me about the net force? And then that'll tell you what it tells you about the work. Ask your neighbor what they put, okay? More have it wrong than right here. So ask your neighbor what they put. See if they're different from you. Ask your neighbor.
I don't even know.
You don't even know?
No, you confused me earlier in the notes.
Okay.
I'll exclude answers.
Right. That's a little bit better. I'm going to stop here at 122. Okay, B is right here. It's 0.
Okay.
It's 0 because the net force, when I read this, constant speed, I say, oh, the acceleration is 0 meters per second squared. That means that the net force is also equal to 0.
Okay, so Right. So, but then when you talked about friction here, you said that it does negative work.
Right. Because I'm talking about a
It also
single.
says constant speed here.
Right. Because I'm talking about a single force. On the previous problem, right here, I was asking for the work that's done by friction alone. And the work that's done by friction is negative. That all by itself is negative work. But this problem is asking something different. You're right that they're similar. They are very, very similar questions. No, not because of the inertia. I have one force.
So if it just asks about friction, then it's negative. If it asks about the total at a constant speed, then it's 0.
Right. All right. So here, the total work that's being done by both of these forces together is going to be 0. Because I know that the sum of the two forces, the vector sum, this one's positive, this one's negative, that the sum of those is going to be equal to 0. And the reason I know that is because it has a constant speed. If it has a constant speed, the acceleration is 0, and so the net force is 0. If it was accelerating, it would be a positive work. Like if it was speeding up, because then, let me write that down in words. So if the acceleration is positive, if it's greater than 0, then the work would also be positive. But if it was decelerating, slowing down, then that means that the work would be what? Negative. Think about work. If I do positive work, I'm giving an object energy. I'm speeding it up. If I do negative work, I'm taking energy away from that object. That's what the positive and negative mean. They mean I'm giving or taking away. Work is a different thing than other vectors that we've dealt with. In fact, it's not a vector at all. Remember, vectors have magnitude and direction. They have a value, and then they have some direction. But work is what we call a scalar quantity. Have we used that word before? Scalar? Work only has a value. There are other quantities that are scalar. Time, mass, charge. Those quantities do not have a direction associated with them. But work is different in that we still give it a positive or negative because it has to do with, am I giving energy or am I taking energy away? It's the work energy here. If I give it energy, I'm doing positive work. If I'm taking it away, I'm doing negative work. Okie dokie? In this case, the frictional force would be this force would be giving energy. But they give and take away at the same amount. So the net force is 0. What is the force, or what is the work done by F in this case? Big F. All right, let's stop at 20. Okay, good. A is right. The work done by F is positive. When an object is moving in this direction, the force F is also in this direction, and so that is a positive work.
On the exam, are you going to put which direction things are moving in? Because then I start to overthink it. I'm like, well, cars don't always have to go in this direction.
Yeah, I'll say moving left or right. It's usually going to be moving left or right. Okay? All right, which of these is a unit for work? I haven't given you the unit for work, but you should be able to figure it out from the expression that we gave that defines what work is. The equation that gives work. All right, let's stop at 32. 32. I'm going to help you out. Y'all are sort of spread around on what the answer is. Remember that work is equal to the force times the distance. So let's try that again. Anytime I ask you for units, then what you do there is you just look at the equation for work. I know the units for force. I know the units for displacement. Then what are my units for work? All right, that's much better. I'm going to stop at 20. Good. A is right. The force is newtons. The distance, or displacement, is meters. That means that A is the right answer. Alrighty? Let me show you another thing that you'll begin to see more on the exams. That I might ask you, what are the basic SI units? And what that means is that I want you to break it down into our MKS system. Remember, MKS, meters, kilogram, seconds. Then I want you to give me the basic SI units in those meters, kilograms, or seconds. And then later, as we move into electricity, we'll see coulombs for charge. But right now, we're just doing meters, kilograms, and seconds. And so I could break these units further down into the meters, kilograms, and seconds. We do that by, again, looking at the equation. I know that force is mass times acceleration. And so those are units of kilograms for mass, meters per second squared for acceleration. So on these questions, what it requires you to do is to know the units for each of the variables, which is a useful thing. You need to know the units for the variables anyway. So for the basic SI units, I need to break down this Newton further. So it's going to be kilogram meter per second squared. And then I have another meters out here. So the basic SI units will be kilogram meter squared per second squared. If I ask for the basic SI units, that's what I'm looking for. Okay? Look back at the old test, you'll see some questions. Increasingly, as we move on from here, as we move past kinematics and Newton's laws and all, we'll begin to see more and more units that build upon one another. And the Newton meter is a good example of that. Another unit of work or energy that you'll see is the Joule. So the units of work and energy are the same. I'm going to call the unit of work the Newton meter, newtons times meters, and I'm going to call the unit of energy as a joule. It's named after a scientist, what was his name? James Joule, I think, that did a lot of work on developing engines and did a lot with power and energy. This is usually abbreviated as a capital J because it's a person's name. So a joule is the same as a Newton meter because, well, they're a little bit different. But as far as we're concerned, we'll say that they're the same. That a Newton meter is the same as the joule because work and energy are so closely related to one another. All right? If you remember, Newton meter, we've seen that before. Y'all remember where we've seen the Newton meter of force times the distance? Think back in chapter 2 or 1. Was it 1?
I think it was chapter 1 where we were talking about motion.
Yeah. Yeah, it was chapter 1. Y'all remember why we talked about the Newton meter?
What to do with leverage?
Yes, you're on the right track. It's a word, it rhymes with dork, perhaps.
Work.
Not work. Work doesn't rhyme with dork. Torque. That's right, Charlie. So yeah, torque, remember, was a distance. That's the moment arm times the force. Yes, remember torque? Torque? Yes. This is not the same as torque. This is completely different from torque. So it's not related to torque at all, even though that's the same unit. All right. Potential energy. So far we've only talked about kinetic energy, the energy of motion. Potential energy is stored energy, or work. Actually, no, that's not right, work. Let's say that it is the energy of position.
Isn't there a special word that they use for it? It was on the
On our quiz?
Configuration?
Yeah.
Yeah.
Oh, yeah.
Configuration.
Yeah, that was from the book. Yeah, I like that. I have this object right here, right? I'm holding it in a particular place, a particular position or configuration. If I let it go, what's going to happen to it? It's going to move, right? So I have this potential for motion. Now, when they talk about configuration, the energy of position or configuration, that'll become important later when we talk about chemical energy. Because if we have, say, some molecules that are all configured in a particular way, they have a certain amount of energy within that molecule. If I was to break apart that molecule, then I could get that energy in some way. Like when you combust fuel in your car, right? That you convert this chemical energy, which is a type of stored or potential energy, into something that's usable. So that's what they mean by configuration when the author writes the configuration. There are lots of different types of potential energy. Elastic, like a rubber band. You ever pop somebody with a rubber band? Pop your sister or whatever, huh? What's that?
It's not tried, I can't do it.
Yeah, I usually just pop myself on the finger. But if you hold it like this and sort of pull it out, just hold it up to their back and go, it pops. Okay? So try that. Elastic, gravitational. We got all sorts of potential energy up in here because we have these forces that are acting between us. And if there were no other forces like holding us in our position, the friction, we would just all suck up to one another. Wouldn't that be cool? If you walked into a room and the gravitational force was so big that you were all had conglomerated into a big ball in the middle of the room. That wouldn't be cool? But that's what happens, right? And when you're forming a star, when you get these really massive objects, and the star attracts all those massive objects around it, and they gradually move around it, and then they'll fall into the center of the star.
Is that what happens to bubbles in a cup?
What?
Is that what happens to bubbles in a cup?
No, bubbles in a cup, that's a different type of force. It's surface tension, that you get these forces between these objects because of the tension in the surface. So gravitational, chemical, like in our gasoline, all of these are potential sources of potential energy. Nuclear, later we'll see electric potential. Later in the semester. So many different types of potential energy, whereas with kinetic energy, it's just, motion.
So you could dot, you go on forever.
But maybe not forever. That's probably about it, actually.
So why is the star thing potential energy?
Because you have a star, and then you have some rock out far away from the star, and there's a gravitational force between them.
Mm-hmm.
Right? There's the potential for motion as the star pulls that rock into its surface. That's how stars grow, right? They accrete matter like that. All right, you move an object of mass m to height h. I want to know what work has been done. Now remember, work is equal to force times distance. And what I'm doing here is I'm taking an object and I'm moving it from h equals 0 up to h. So I'm moving it up to this height in this direction. And I want to know what work has been done here. So your key is to find out what is the force. Or what force is required to move this from here up to here. And then if you multiply that force times the distance, then you have your answer. We'll say that this object has a mass m. All right, let's stop at 107. 107. Good. C is right. Because the force, remember gravitational force, this force is equal to m times g. And so the work is equal to m times g times h. And so that gives us our expression for potential energy. That this work has given it potential energy. And so the potential energy is equal to m times g times h. All right? That's the variable that we'll use, yeah. But sometimes I use PE. Did I use PE before? Yeah, U is usually for potential energy. Now remember, we have two types of energy so far, and I'm giving you two equations. K is for kinetic, that's 1/2 mv squared. And then U is potential, that's mgh. So those are two sort of fundamental equations for energy. And they'll become fairly important.
But that mgh only applies to gravitational, correct?
Right, that's our gravitational potential energy. Notice here that what we did is that we applied work to an object, and when we apply work to that object, it gave the object energy. So if I take this object and it weighs, a few newtons, and I apply those 3 newtons of force in order to bring it up here, it now has potential energy. And I can convert all that energy, all the potential energy that I gave it, back to kinetic by doing what?
Letting go.
It changes it all back to kinetic energy. It speeds up. So potential, kinetic energy. Potential, kinetic. Okay, H refers to the distance. Don't worry too much about the reference point. We will always take the reference point as the ground. So we will always say that the ground is h equals 0, and then some height up here is our height h. Though if you take a more advanced physics class, I expect y'all won't, but if you do, you'll find that that we can move that reference point, that it doesn't have to be at the ground.
So, like the table, for example, or...
Yeah, that's a good example. Right here, we set our reference point to be the table, not the ground. And I say that at this point, the object has no potential energy, but then up here, it has more than 0 potential energy. Now, even though the ground is down here, that I've chosen this as my reference point. You understand? You follow?
So if the ground was still your reference point and the book was sitting on there, it would still have potential.
It would have potential energy, and I would just have to do this, right, to convert it to kinetic energy. All right. When you... What's that? Oh, yeah. I think that's from the book. When you drop the object, just like we did, the U is converted to K. All right, let's try these. What factor does the kinetic energy of a car change when its speed is triple? All right, stop at 38. C is right here. Remember, kinetic energy is equal to 1/2 mv squared. If I triple v, I multiply this by 9.
Worry about the half, because I had that part first, and then I was going to half it.
Right, don't worry about the half. Yeah,
Oh, that's true, that's just coefficient.
it's just a coefficient, right? Let's try this one. Think about this one. Which takes more energy? To go from 0 to 30 miles an hour in your car, or 30 to 60 miles an hour? I want you to remember the graph that I drew earlier. Remember I drew a graph of kinetic energy and speed, and it looked like this. It's a parabola, quadratic. So what does that tell us about the energy that's required to go from 0 to 30, 0 to 30, and then 30 to 60? All right, let's stop at 105, 105. All right, the answer here is B. Yes. Yeah, look at this graph, okay? Let's put in some numbers here on this graph. I'm going to say this is 0, this is 30 miles an hour, and this is 60. When we read this graph, we look at, well, to go from 0 to 30, I just need this amount of energy. Right, I'm going from 0 to 30. So I just need this amount of energy. That's a curly Q bracket. But then to go from 30 to 60, I need that amount of energy. That's a lot more energy, right? And the reason is because it's a quadratic relationship. That when I square the velocity, as the velocity gets bigger and bigger and bigger, the kinetic energy gets even bigger and bigger and bigger. Okay? That's why your car gets poorer gas mileage at higher speeds. And part of your car is just it's designed to travel at a particular speed, and it gets the best gas mileage there, like at 45 or whatever, 50 miles an hour. But as you go faster and faster, if you're going 70, 80, 90 miles an hour on the interstate, you should be going 90 miles an hour. But if you're going that fast on the interstate, you use up a lot more gas.
Is that why Volkswagen had that big issue that they did, was because they lied about
Oh, yeah. I don't remember. I'm not sure.
They lied about being fuel efficient with their diesel.
Mm-hmm.
They were saying you could get so many miles to the gallon, but it was not like unrealistic.
Yeah, maybe so. But this is more fundamental. That if I increase my speed, it takes a lot more energy. Okay? If I'm going 90 miles an hour as opposed to 45 miles an hour, look, that's a big difference in energy. Actually, would be like 90 would be here and 45 would be here. So it's twice as much. Okie dokie? So exploring that idea that it's a quadratic relationship, and think about how those variables change with respect to one another. Other types of energy. Mechanical energy is the sum of U and K. Remember, U is potential, K is kinetic.
Why do they use U?
Because P is used a lot in physics. P is used for pressure, it's used for momentum, which we didn't cover. It's used for something else. Huh? Yeah, because M is used for other things. We didn't do momentum though, don't worry about that. I don't know, U is just, it's a normal way. Sometimes I'll not use U, I use PE and KE. But get into the habit of using U and K, because that's what the author of the book uses. And that's sort of more standard. All right, so E is U plus K. Considers energy from position and motion. Right, position, that's U. Motion is K. And there's a law, the law of conservation of mechanical energy. And what it says is that energy transforms from U to K and vice versa. But the total energy remains the same. So we've seen that already, right? That if I have this thing, it has potential energy. If I let it go, it converts that to kinetic energy. But the total amount of energy that I have in this object from here to here will always be the same. If it has 10 joules of energy up here in potential energy, then it'll still have 10 joules of energy down here. So let's look at this roller coaster. And I'll have some questions. Well, here, we'll do them as clicker questions. The first one is, where is the kinetic energy the greatest? You know how a roller coaster works, right? You have this thing, you go off the edge. And I want to know, where is the kinetic energy the greatest? At A, B, C, or D? Okay, good. Doing well. Just a few of you have the wrong answer. Ask around if you like. See what your neighbor put. All right, just a few more seconds. Let's stop at 45. Good. D is right. The kinetic energy is greatest because that's where he's going the fastest. And down here, U is equal to 0, basically, and kinetic energy is at its maximum. Why is U equal to 0? Remember, U is equal to M times G times H. And if H is equal to 0, that means the potential energy is equal to 0. All right?
So you know it's up off the ground.
But yeah, we'll say sort of this is the ground. But it's definitely less potential energy than either of these points. I mean, less kinetic energy than any of those points.
So, is one of those things where one of them is the greatest and one of the other's not?
Right.
Vice versa.
Mm-hmm.
You can't have them at the same time?
Yeah, you can have kinetic and potential energy at the same time. Is that what you're asking?
No, like one's going to be higher and one's going to be lower. They're not going to be both higher and both low.
It's like a trade-off. So if I have 10 joules of energy at the beginning, I'll always have 10 joules of energy. Sometimes I might have 10 joules of potential and no kinetic. Sometimes I might have 10 joules of kinetic and no potential. Or I might have somewhere in between. Like I might have 5 and 5 joules. But the sum of those will always be the same. That's what this law says right here. That the sum of U and K is always constant.
It explains it really well.
Mhm.
It's good for me.
Yeah, the book is a really good resource. All right, where is U the greatest here? At A, B, C, or D? All right, let's stop at 142. 142. Almost everybody has it right. That's awesome. U is the greatest at A, right? Because H up here is at its max, and V is equal to 0. That's right before the cart goes off the side of the, or goes, down. So U is at its maximum at point A. Very, very good. I met this lady the other day. She swore up and down that she had seen me, that she had met me somewhere. In fact, she said that she had met me at the meeting of the Vegetarian Club. Never seen her before. I don't think y'all appreciate my jokes. Like, that was a good joke. That was funny. You get it? Herbivore? Never seen her before? Never seen her before? Alright, where are U and K equal? So remember, we can have this, or we can also have this, where they're roughly the same.
Are you a vegetarian?
No. That wasn't a real story.
I know you said that you like carrots.
I do like carrots.
Are we in the third one already?
Yeah, where are U and K equal? I understand. Hmm? I get us 7 o'clock. I slept in. I got up at 4. All right, let's stop at 50. Look at y'all. C is right. Very good. Oh, Kate. Yeah. So if I'm looking at, let's say that this is potential and this is kinetic. At A, it looks like that. At B, it looks like that. I have more kinetic energy. At C, it's like that. And then at D, which one was potential? Was this potential?
Yeah.
Okay, at D, it's like this. Like, it's going fast. It has less potential and more kinetic. But not as much kinetic as it had here. This is the fastest point. This is the slowest point. In fact, can you rate these? Can you rank them from fastest to slowest? Try that. That's a good test question, too. Rank A, B, C, and D from the fastest to the slowest. What's the fastest?
Speed.
Fastest speed to the slowest speed.
B, D, C, and A.
That's right. B, D, C, and A. Fastest, next fastest, slowest. Next, the third, and then the slowest of all. So fastest to slowest. See, this is C. Fastest to slow would be, what do we say? Yeah, B, D, C, A.
Why D?
Huh?
Why D?
D, what about D?
Why is D the second fastest?
Oh, because D is the fastest because it's the lowest. So it has the least potential energy, the most kinetic energy.
And you just got done coming off of the giant hill.
Right. This is the next fastest because it's just a little bit higher. It has a little more potential energy, and it still has a lot of kinetic energy. And this one has even more potential energy, so less kinetic energy. And this one has basically no kinetic energy, it's all potential energy. So I could also say fastest to slowest. I could say biggest K to least K. Alrighty? Look, the next couple pages are pretty quick. So I'm fairly certain that we'll get into up to page 43, I think, in your notes. That's up to energy in the body for the test. So go ahead and start planning for that as you're preparing for the test on Tuesday. And I'll start preparing it as well. Okay? Read your book. Your book is a good resource for this test. Looking at the old quizzes, the old exams, good resource. I want a good showing on this exam. Test is Tuesday, okay?